deeply into a couple of topics. That could be a gravitational wave or merger remnant and electromagnetic counterpart. So as I was explaining at lunch, I had to motivate for many years why I'm doing gravitational wave. Today I don't have to. I simply put a slide and everyone recognizes it. Or in any case, aware the neutron star merger detected in gravitational wave and magnetic bands on August 2017. So I don't go in detail into this observation. I will say something later. We use it, of course, to benchmark the theory now. But basically, our task is to try to model this type of observation from first principle. And first principle, when it comes from neutron star, means strong gravity, so general relativity, plus magnetic field, plus neutrino, plus nuclear physics. In a nutshell, what's the field of numerical relativity? Yes, it's the simulation, or a complicated simulation of strong gravity astrophysical events. But if we want to say a bit more, it's a very interdisciplinary field. So we have analytical, strong formal and mathematical aspects, like the formulation of general relativity as an initial-line problem, how to formulate in general relativity hydrodynamics and Boltzmann equations, as you understand, challenging aspect and challenging equation. There's a feature of general relativity that becomes also a feature of numerical relativity. So what coordinate do you use? And of course, the computer cannot simulate singularities. So we need to deal with that and to come up with creative ways of choosing our singularity. And I won't say much, but if you're interested, you can of course elaborate. And there's of course the computational part in which we do have to solve a difficult, complicated PDE system that has even characters that we don't know. And maybe we need to simulate multi-scale. So we need adaptive grids, and we need, of course, parallel computing. So it's very difficult, and it's also very interesting, especially for students, to get into the field, and they can learn many different aspects. Everything that I will talk about today, it's based on, I think, what is the largest simulation campaign or simulation set of binary neutron stars. So here, these are all simulations. We have actually doubled this by now, and they are all publicly available. These are different quantities. I will not comment, but here every dot is a simulation. Okay, and so we span different masses, different mass ratio, different equational state, different resolution, which is very important to control the result, and different equational state that you will see if you interact with some names. This is all public release in terms of waveforms, the observable, and also in terms of certain quantities that are connected to the electromagnetic observable. So the advertisement is off. Okay. No. Okay, so what is the picture that emerged from 20 years plus of this simulation? Well, the picture is sketched here, and I could talk for hours about this diagram. So essentially, what we know, what we expect, is that neutron star somehow forms from supernova collapse. The binaries are polarized. This is a result, it's known from the 60s. And so in the last, say, minutes of life of this binary, when this binary entered the ground-based band, the ground-based interferometer band, this is almost circular orbit, but of course there's a radiation reaction. So this is actually an spiral, okay, that inevitably ends with the collision of the two stars. So this is called transition from the spiral that goes from minute to actually millisecond time scale to merger that happens on millisecond time scale. So stellar mass object 30 and kilometer radius that merge on fraction of velocity of light and on time scale of milliseconds, quite a powerful event. And they emit gravitational wave. So the initial part of the story is essentially dominated by gravitational interaction, radiation interaction. Then, of course, when the stars are getting in contact, you may get different merger product. Okay, so you get a phase that is very dynamical. It is initially still, this is called the post-merger phase. The initial phase is still dominated by the time scale of the gravitational radiation. This is because this object is highly distorted in some sense. It has a rapidly variable for a moment. And this is the phase, for example, where matter can be ejected. So neutron-rich barium matter ejected from the collision or from the tidal state. This is called dynamic ejecta. This gravitational wave dominated phase more or less has a typical time scale of about tens of milliseconds, after which all the gravitational wave is effectively radiated, and the binary slowly enter much longer viscous phase, in which the dynamics is typically dominated by other processes. Could be turbulence, could be accretion, and so on and so forth. We will discuss some of these things. In any stage, in any post-merger stage, of course, it can be gravitational collapse, so you can get a black hole. But it's also possible to obtain a stable star, for instance, when the initial masses are particularly low. So all the detail of this actually depends, say, on the progenitor. So there is no unique way to go to here or there. There are different ways. It depends on the masses, on the particular equational state, and so on and so forth. At the other stage, there is emission of matter, for instance, in terms of winds from the disks. And finally, a very long term, the expectations that there will be somehow black hole collapse. In those cases, there will be the jet forming. That's the unknown moment, camera bars emerging from the remnant. So, as you might have guessed from the graphics, especially after merger, you have all the interaction playing a role here. These are all in extreme conditions, so extreme densities, but also temperature, as we shall see. There are dynamic instability developing and determining, for instance, the degree of turbulence in the winds, which is very, very important. And then, of course, we can actually change the composition of the matter, and they are critical as well.
So, Sebastiano,
yeah.
Two questions. So, what did you say? It circularizes. Is that always the case? Can you have highly eccentric?
So, according to standard formation channels, it's always the case. If you have isolated binary
so that's
on many years of evolution, then yeah, it's a simple calculation, and this is radiated at the very beginning, and before the merging time, this will be almost perfectly circular. So eccentricity up to -5 and -4.
with black holes, you would have highly eccentric.
So if the formation channel is different, yeah, as I'm told, then you can have other type of eccentricity. But for this particular standard scenario, you would expect perfectly circular, and that's what we observed.
Just as the formation channel for neutron stars, that would be very rare, right? That would give you eccentricity because you expect that binary neutrons come from two stars that were already.
That's right. Yeah, people have looked into the sort of rates you expect from capture dynamical formation, and extremely low.
Yeah.
So they suspect that most of the binary neutron stars form from massive binary stars, and then they should be circular indeed.
I see. So that's in contrast to the case of black holes.
Yeah, black hole, it might be 50-50.
Okay. And then the other thing is, in the case that the final state contains a black hole, can it really take 10 seconds to get there as opposed to just milliseconds?
It can take many seconds. Actually, this picture is reasonably well known up to this level. So up to this initial viscous phase, that is not well known. So we know how to predict black hole formation at merger. So if they are particularly massive, for example, then this is completely under control. And we have a very good and quantitative understanding of when it happens based on the progenitors, and less quantitative when we go to different mass ratio, because there is determined by tidal disruptions, which is a little less useful. But then everything can happen. And so in principle, yes, it could. So a black hole could form much later, maybe after 100 milliseconds, after a second.
So you have simulations that give either a final neutron star or a final black hole?
Yes.
In 9 milliseconds.
No, there exists only one simulation that goes to 1 second. And provided that you trust the physics that is simulated there, that's the longest that is available. But typically, the typical simulation that I'm going to show today, they go to hundreds of milliseconds. And the challenge is not pushing a simulation. The challenge is to have the right physics and to get it right and trust it at such a long time.
But there's also computational cost aspect to it.
There's computational cost. I would say that the challenge is more to get the physics right.
But you can trust it, mean that the resolution is enough to capture the physics?
Yes, the resolution has to be enough, but typically this is what we work on, so we run a different resolution. But for instance, there are different ways of including with interaction.
Including with interactions in your simulations?
Yes. So for instance, there are different ways to do neutrino transport.
Are you going to explain this in detail?
If you want, yes, I have slides. If there is time. For instance, we know that magnetic field amplifiers, and they amplify at this stage, the shear interface of the collisional interface, but they amplify also in the disk through MRI. And well, do we resolve that? That is hard to resolve. These are small scale, high density. So you can perhaps run very long simulation, but you have to make sure that you amplify correctly these magnetic fields. Otherwise, for instance, you might not have jet injection. So all these aspects are tricky to have and control.
Can I ask a simple question? So you said that you can delay the collapse to a black hole up to a second after the.
So nobody has ever done that, but there might be cases in which there might be delayed collapse.
For as long as a second.
No, I don't know, but it has never been explored, right? So
I suppose that if it's true that you can, sorry.
But I suppose the phase of accretion from a disk that is light after that, they need to more efficient and formation of a hole.
this is one. So I have a very advanced slide later. But what happens is that essentially what we find is that okay, I'll talk about this later.
Yeah.
How robust is the dynamical ejecta you are mentioning? How robust is this? The conclusions that you come from? Do they depend on, for example, resolution? Or
I didn't get it.
the dynamical ejecta that happens.
So this is the first episode in which some material can become unbound, and typically this can happen. This I do. Sorry, it's spoiled. And this can happen for two mechanisms. This is that, but it's good if we do it interactive. It's better. Yeah, so this is a nice visualization on one of such collision, and these are the two cores, but they have already merged. And essentially, this material can become bound by tidal forces, centrifugal effects from these states, or precisely from the shock between the two cores. This is pictured here. Okay, so this is the density of the maximum density of the remnant, which oscillates because these cores are bouncing at the beginning. And this one instead is the emission of the mass that is emitted. And you see that it starts to take over after the first bounce. So this is one of the mechanisms for which is, according to which the matter is ejected. And the other mechanism is this simply kinematic centrifugal effect. And this is the mass emitted in one channel, and this is mass more or less emitted in the other channel. These are all binaries. You see, it's not 50-50 because it depends on how deformable is the star, for example, depends on the mass ratio and so on. But for vanilla comparable masses, binary neutron star, typically the component emitted from the shock is larger. So this is how this dynamical ejecta comes
So
about.
from that note, I guess so we can get the conclusion that this is a robust phenomenon.
It's extremely yes. Sorry.
In order way.
Sorry.
Can we go on in an order way?
Yes, since he asked the question. Yeah, it's extremely robust and it's observed in all the simulations. Even this is observed also in Newtonian simulation, for example. Okay, so in order, let's go back to the slides. Okay, this is more or less a story. There are more things that we can discuss. Here comes the first question for us, for me, what do we do? We are interested in gravitational wave. We are interested in modeling gravitational wave, especially from this phase that is gravitational wave dominated. And for binary neutron star, what we can do at the moment is to predict the spectrum quite accurately. And it has basically this form. So this is the gravitational spectrum as a function of frequency. So this is the frequency band of the ground-based interferometers. This enters the ground-based interferometer, and this straight line in this log, this is the chirp signal. So frequency goes up, amplitude goes up. In this plot, it's a line that goes down in the spectrum. Then here there is merger. There is merger. This process of collision. And then if there is a remnant, there is kilohertz emission also from the remnant. And yeah, one of the questions that we ask ourselves is how do we obtain this complete spectrum? And I will try to explain some of the things that we do. Typically, the strategy is to combine some analytical approach to the two-body generalistic problem with simulations. And essentially, the analytical part works at lower frequency. It gives you a pretty capable description at lower frequency, and in principle up to merger, whereas the numerical part gives you, of course, a description of the remnant and goes back up to the point where you can start the simulation. So there's a region of overlap in which you can combine these two approaches and obtain actually. And I will say something about that later. Then what do you do with the spectrum? But for example, one of the things that have interested people since 2017, but even before, is if from this observation we can say something about the neutron star mass, particularly the equation state. And I think I have something next. And another question is, okay, but what is the accuracy? So one point that I want to stress is that to do this type of science, you really need a very, very precise model of this type. And we are not yet there. So this is an example. We'll discuss more at this time, but this is an example of what you can do if you have a full spectrum model. And essentially what you can do, what we have demonstrated here with Bayesian analysis, is that you can constrain the mass-reduced diagram of neutron stars. So the gray part is what we know after pulsars measurements, after the event of 2017. And for this work, what we have imagined is, okay, let's say that tomorrow Einstein telescope is activated, and we get a single signal, which say corresponds to the state. And of this single signal, we detect the entire spectrum in such a way that we can detect inspiral-merger as usual, as always possible with Einstein telescope, but also the kilohertz emission at a minimum signal-to-noise ratio for detection. Okay? So if we do only the inspiral-merger detection, what we would find is this magenta area. So we would shrink the gray area and learn more about the mass of this area. But you see that we would not capture, for example, the maximum mass. Essentially, this is a 1.4, 1.4 is most informative. Solar mass is most informative in this density region. Right? But if we add kilohertz observation at the minimum signal to noise ratio for detection, you see that we would capture also the maximum mass, and in particular at the precision that is about 10%, 15%. So this is one of the things that we could do with that Einstein telescope, with the binary light, with an additional observation, single additional observation by 17 once. And I might show more later. So since we are talking about matter, this is a sketch of what we think the matter in a merger collision behaves. In each row, there are 3 phases that I named before. So a late inspired phase, gravitational driven phase, and early distance phase. These are snapshots of mass density, so you can imagine this is actually the density distribution of the stars. And these are more interesting plots. These are histograms in which we put the density and temperature, or density and electron fraction. And each bin here, each dot, is how much mass is in this particular condition, is in this particular thermodynamical condition. So here there is a lot, it's dark, there is a lot of mass, about 10 to 15 grams per cubic centimeter, and about, I don't know, few tens of millimeters. So these are useful to study our prediction, of course, based on the nuclear model that we employ here for the thermodynamic condition. So during this, very quickly, during the spiral, what you get is certain high density stars, mostly in beta equilibrium. Okay, this go around, and temperature, there are some effects that you can consider this temperature almost zero thermal temperature. Then, of course, the circle light, this is the violent phase. You see this, there are, if we would animate this, you would see 2 cores that are bouncing back and forth. You have the spiral arms and so on. So what happens in the thermodynamical space? Well, it happens that this is log, so you don't see it much, that the density goes up to factor 2. And we start with high values. The temperature goes up because you have a shock collision between the 2 cores, and it goes up to actually 100 of MeV. Here you see that where the stars are hot is not where the stars are dense. Okay? So star gets hot at the collision interface, which is not the highest density region. And then what happens is that in this interface, it expands, generate the spiral arcs that of course expand outwards, emit neutrino, cool down adiabatic processes, and that's why you see this spread here. Okay, some of this matter, especially this one, at the very low temperature and lower density, is the matter that actually becomes unbound. So if you want to know what the condition in the ejecta are, one has to look at this part of the end. Again, if you animate, you will see the strings really flowing in this. These are animated on YouTube. And at the same time, you have high temperature, you have neutrino, you have magnetic fields, you have neutrino and matter interaction. And so you see that suddenly this is mostly beta type of decay. So neutron beta decay and neutron positron capture. So the net effect is that the neutron-rich matter at the beginning gets more and more protonized. Okay? And then you see why the electron fraction, for instance, raises. And this raises in particular here below certain typical densities, whereas the core quite remain in approximate typical. So this is very dynamic, but wash out very quickly, and you enter another phase, in which in this case you have a neutron surrounded by this, which you see here, the neutron star, and then you have material that is orbiting around, eventually and so on and so forth. And here the interesting part is that this disk can either accrete if there's a black hole, but in this case can also evaporate. And one way to evaporate is to emit more and more energy for momentum. And one mechanism that acts very quickly are the spiral arms that transport. This is a general feature of this type of physical flow. Spiral arm that transports angular momentum outwards, enter, of course, the disk from the remnant, enter the disk, and then in outer part of the disk, this gets expanded or inflated. And what we have in the simulation is typical production of alpha nuclei, which releases energy and releases also some mass. So this is what we call this spiral wave wind, which is a first process that emits even more matter from the remnant. And of course, it could be on longer times, it could be more and more processes, but they are all based on a delicate balance between the turbulence that develops in the disk and maybe the neutrino eating and the accretion that the disk itself has towards the central object. And so they depend also on the central object.
Yes. You're explaining these graphs, which I had a hard time first figuring out what the axis were. But then so there's something here that one sees. There's a clear line with where is that coming from? Is that the wavelet state or
Which line? This?
So for instance, that picture and the picture above, I see something with a very slow. So that's temperature going as some linear density.
Yeah, it's log, so this is a certain power.
So it's some power.
Yeah,
Is that does that correspond to the wavelet state of?
Not exactly, but it's like a standard. You can get approximately the power by standard diabatic expansion.
So it's that follows from a diabatic expansion.
Mostly.
What fraction of the mass does the ejecta represent?
So in this first dynamical ejecta, it's about 10 to the -3, 10 to the -4, so it's not much. But this is important because it's also the most neutron-rich typically. So it's the one that, as I'm now going to show, is gonna to undergo our process of synthesis and produce up to analysis for it. The mass on the disk could be much more in principle, but this strongly depends on the precise configuration. So whether the central object is a neutron star or a black hole, and what's the accretion rate at the very beginning, which if there is a black hole can be very high. If there is the spiral wind, for instance, if this develops or not. So we have some upper limits here, but it really depends on the configuration. Which means that can give also very different observable, which means that from the observable you might be limited. Yeah, so this is the reason why we talk about mass ejecta and nuclear synthesis. So it was proposed a long time ago that this is neutron-rich matter that expands and decompresses, and naturally is candidate for site for our process, nuclear synthesis, for the process. And nowadays, I think it's accepted that these mergers are, if not the entire, but a good fraction accounting for a good fraction of the heavy elements that are produced. And yeah, the typical sketchy thing is that you have a lot of neutrons, you have rapid neutron capture, you have decay, this so beta decay nuclei force, and so you can get easily from almost any solution, you can easily reproduce abundances similar to the solar system. So this is a very robust result. What is less clear is that this is supposed to be accompanied by well, electromagnetic transient. that was postulated already in some of the initial, or was studied in some of the initial work, but of course nobody has ever seen it. It was under the name of kilonova, but that is actually what has been observed in 2017 and clearly recognized because it's associated to the gravitational wave. So it's an optical near-infrared type of transient that is characteristic, is weaker than supernova, and it's here. So this is a simulation of the nuclei. This is the thing that we observe. So it goes on days, month time scales, and this corresponds to the essentially that has been observed. So it's something that goes out of the scale of this picture, of course. It's something that but starts from this dynamical ejecta, and there's these widths, right? They're initially opaque, they expand, they undergo process nucleosynthesis, nuclei are formed, they keep on expanding, they will become transparent at some point on days, month time scale, and then you start shine and get the observation.
And so we say that this last space is something that's well understood. So it's
I don't think this is this is definitely not understood. There's a lot of uncertainty here at the atomic nuclear level, and you can of course assume some ballpark number.
To start, let's say some initial that the world after this thing has got some
Yes.
distance from
So-
there, and that's say that should be well understood. I'm saying no.
No, so you can pick some of
No,
these.
I take some later phase.
Yes.
Okay?
And take some numbers.
That,
Yes.
there's parts of that which are a mess, but you have when the picture looks more messy, and that should be messy. And then when you go later,
Yeah, so what people have done is to take a ballpark number for the velocity of the spherical ejecta shell, right? Ballpark number for the mass, ballpark number for the capacity, and so on. But they have shown that the entire process is very complicated. There's millions of lines. There's a lot of atomic uncertainty, and they have shown that I don't tell you all the details, but they have shown that by varying the different atomic models, for example, they can have order of magnitude uncertainties here in these light groups.
so they are saying is that curves from some point on, they look fairly structureless. So I would say that that's something that should be fairly linear, fairly structureless, so that part, not the initial part, the initial part that's missing. At some point on,
So the ballpark can be fixed, and I think that some property are fairly robust. So it's not that we don't understand it. I mean, there's a clear identification. So, but the details of it, I don't think they are.
so if I start from the units 10, I don't know what units are that.
Days.
These are days, okay, well, I just say days. So from then 10 days on, you say that if I give you the curves up to that point, you cannot predict how they follow?
I'm not sure. This is really radiation transfer simulation, right? It's similar. These are light groups similar to supernova light groups. So there's quite a lot of physics that go into it, and they are ultimately determined by, of course.
But I thought this curve just come from the radioactive decay of the nucleus, right? So slope, you see the change in slope.
This is a combination of cocktail. This is not just one final nucleus, but it's not like a supernova. Like this is a power law in time, it's an exponential power law.
Sure.
Okay, power law that comes from the cocktail of all the other meetings.
So there's not much understanding of all this transition is very complicated, and it's not like on spot that it's this or that or whatever. So one of the things that, of course, we want to do is to, well, these things do depend on the remnants. So we want to be able to predict the remnants. We also want to understand the different ejecta mechanism, because that comes with different property for the ejecta. So how much electron fraction is a certain type of ejecta, how much neutron rich is another. For instance, there's a point is a bit hidden here. There's an early blue point. Nobody has been able to fit with anything, but it's a very precise measurement. So this has also, trigger discussion on how do we produce particularly blue. Also, this you see a lot of blue here. This color was something that was not entirely unexpected. It was not entirely expected. So in July, August, July, there was a conference was there, and they bet that they would never see a blue kilonova. Right? So yeah, we want to understand how these ejecta are calculated, because these are the preconditions to then understand processes that produce those light curves. And finally, yet another question could be, okay, how do we use this in combination with gravitational waves to learn something more about the source? Now let me go back. This is the same plot as before, the mass radius background. We don't add artificially now a new event, but we simply take the gravitational wave event and analyze the gravitational wave data together with this data set of kilonova data. And through a process that I will present here by the end of the talk, if we have time, we can further shrink the possible region in the mass reduced diagram if we add and analyze the electromagnetic data. Of course, the link here is not obvious. The link is provided by the simulation that I showed you before. So there is a way, or we have found a way to connect the binary progenitors with some ejecta properties, such that through a kilonova model, we can go back to the mass radius diagram of the new star. And of course, if you like, the student was very excited about that. He added nicer observation, and the thing shrinks even more. So these are currently all the constraints that we have from physics on the mass radius diagram. And if you focus as a representative quantity, the radius at 1.4 solar mass, so something here, you have an uncertainty of all of that. You have 12 with an uncertainty of plus minus half a kilometer, 700. And of course, many people work on that. And these are all the measurements done with different technique, taking similar idea or even just nicer data, and so on and so forth. And all these measurements are more or less agreeing and perhaps a bit improving or converging towards a radius that is about 12, that I'm told that's a significant number for those developing in the gravitational state. So, a few more things to showcase if we have sufficient understanding from numerical relativity simulation. Well, what we have done here, a bit as an exercise, this is a full ab initio calculation of the spectra. So we have provided the simulation and work some of the physicists, and we have provided simulation that are targeted that particular binary observing nodes. We have calculated this ejecta. We have calculated the nuclear network, so see how much elements have been produced, injected all the information into radiation transfer code, calculate the spectra, and that's what we found. So it's pretty much matching the observation. This is completely theoretical. This is an example of an exercise. And we have also reproduced this feature of the strontium that was identifying the actual data observation. So it's a nice cross-check of this important result that comes from full, and they're only for the moment.
Did this pose any constraints?
No, the only thing that we did here, so there are a few approximations on the way,
Yeah,
right?
sure.
But the only thing that we did here was to take the initial masses correctly, have lunch of very different equation state just to span possibilities, and around the simulation, extract the trajectory of the ejecta around the neutron network, and then run their.
But the data doesn't constrain the operations of state.
No, in this case, no, because it's taken that is already compatible with the gravitational
Yeah.
wave event, if you want. So we've taken the masses from the gravitational wave event and managed to reproduce an electromagnetic spectrum, so another type of application.
The nucleosynthesis is run on top of the trajectory.
This nucleosynthesis is run on top of that. Of course, it's very hard to do it online. It's one of the targets that we have. But the good thing is that it doesn't seem so sensitive. So I think it's a common finding. So it's much more, the abundances are fine. What you would like to have in principle is the heating back in the fluid, which will make a difference in the simulation. So that's what many people want, are running after. And I think there are some very preliminary study, and that's good. So we will manage to have that. I'm not sure if we will have the entire, but within certain approximation, we will be able to do it. So, but yeah, the eating, it's actually important. This has been shown by Stefan Ross, for example. And finally, last example of how this simulation can be helpful is this. So 3 years after the merger, to 2020, there were observation of, again, the same source, and at 1 Kelvin, at 1 TV, and it seemed that the flux was brightening. So these are the 3 new observations. This is the afterglow of the GRP, and it seemed that there was a brightening. So people ask, okay, what could be that? And one possibility, many possibilities, but one possibility is actually suggested by the simulation. So this is a kilonova afterglow. So the mechanism there would be that from the dynamical ejecta, there's a tail that is very, very high speed. And it's very little matter, but it's really emitted up to, I don't know, above 0.5 C. And that, of course, can it takes time quickly and can finally do synchrotron radiation when it is decelerated against the interstellar medium, for example. And again, we use these people took our simulation and analyze as best they could. And the result was that this small rebrightening might be compatible with such a kilonova afterglow. There are more observations by now. People are less optimistic, but the prediction is there. So the prediction is there, and if you wait long enough, at some point, you will certainly be able to prove whether you have kilonova afterglow from this high-speed tails of the dynamic ejecta. In fact, some recent models says that they expect something 10 years. We don't know, but there is a clear prediction that could be already tested here. It will require a bit more. Okay, how long?
Well, we've done all the questions already, so 5 more minutes, I would say. Then we have a full hour.
Oh, okay. No, because I will start to go in detail now.
You just started it.
So let me perhaps no. If I have 5 minutes, maybe I can conclude and take more questions.
I'm fine if you take a bit more time, but I know some others might be time constrained.
I think we might let him conclude, and then whoever has to leave to teach or whatever can leave.
Yeah.
Anyone who wants to stay can stay.
Yeah, that sounds good.
So for those interested, we could talk a lot about how do we model gravitational wave. We do something very technical, but let's skip over that. So private parameters, simulations, patterns. something neat. Here, this I think is something interesting because to conclude, I would like to say something. Okay, but you have done everything. What's left over? Right? No, it's not true. So in particular, I briefly discussed the variety. That is important of neutrinos. The variety of remnants that you can get. So this is, for instance, the disks, the remnant disk. In the case of a neutron star remnant, in the case of the black hole remnants, it's pretty obvious. This are more compact. They are more proton rich. These are more extended, more neutron rich. So this determines different type of emission in the future. But this is one aspect that I think would certainly deserve a lot of work in the future. So what we generically find after these hundreds of milliseconds of evolutions is that the remnant has typically angular momentum and mass in excess. With respect to what? Well, with respect to equilibrium neutron stars for the same baryon mass, with the same baryons inside. Okay, so this is described in this diagram. It's a simple diagram. This is the baryon mass, so the main baryons. This is the angular momentum. And this gray area are the equilibrium configuration, the general relativistic equilibrium configuration of the rotating neutron star. Okay, so they cover, the stable one cover only this area here. So we can compare our neutron star merger remnant with equilibrium configuration with single mass, for example. And what we find is that all, this is case for one, but all the configuration lay on the right of this region. It means that they have more angular momentum, and also many of those are still on top. It means they have more angular momentum and more mass. So the question is whether these are stable objects or not. And well, the evolution in a simulation would more or less proceed in this way, because the binary remnant stays at a constant, more or less constant baryon mass during the gravitational wave phase. So you don't have particle matter. Then, of course, as it starts to eject matter, the baryon mass goes down. And this is already under and so many seconds, so we can only project this into the second evolution. But what this diagram tells you is that if you start here and say, this is a very high mass, so must make a black hole. Well, this diagram tells you that not necessarily. It could lose enough mass through winds to enter, even if it's very massive at the beginning. It could lose enough mass to enter the stable branch and be a stable millisecond producer or something like that. So it's a counterexample. This is completely open, but of the thing that can happen. So of course it could also not shed enough mass and stop there and make a black hole after a long time. So this is one of the things that I think would be for the future to understand more or less what happens. And here we know what governs these processes, but these are complicated processes. So you have neutrino cooling that of course favors somehow accretion, but you have also viscous processes like turbulence, magnetic stresses, neutrino reabsorption that tends to inflate whatever material is there and eventually allow it to be unbound, right? And this is what I mentioned before. Because there's nuclear combination of a particle, you would expect massive winds. So it's a delicate process to understand, but and you have to simulate the right physics at the right resolution. That it's one of the things that is completely open. So this we cannot predict. We can perhaps predict prompt black hole formation at merger, but not yet this.
One question about this block. Why baryon mass on the left and mass on the right?
This is baryon mass, and this is gravitational mass. So just different type of masses.
So what is the definition of baryon mass?
So baryon mass is the number of baryons, and it's a conserved quantity. The gravitational mass can change.
Wait, but the number of variants is a few number. Do you mean the number of variants times mass of both?
Yes. Yeah.
And that's higher than the gravitational mass because you're not because of the binding.
Typically, yes, because of the and this is the gravitational mass. So it's something that you can lose in gravitational wave.
So in that diagram, the highest mass is 2.7, 2.68 or something. That seems pretty high for the maximum.
0.7, 1.35, 1.35 each.
Because of rotation. Sorry.
Yes.
Yes. Because of rotation.
This is another interesting thing. The remnant is not, the core of the remnant is not rapidly rotating. This has been shown many times in the simulation. What happens here, you have a remnant that is differentially rotating, where you have a core that is static, almost static, stationary. And then you have this mantle or a large disk around that rotates around. But for instance, another thing that what we find is that if there is black hole formation on short time scale after mergers, it is tens of milliseconds, gravitational wave dominated phase, then the collapse typically happen at a density which is slightly below the TOV maximum density. So it's slightly below the maximum density of supported by equilibria of non-rotating units. So that's another thing. So it's differentially rotating as a global thing, as a remnant, but most of the mass is actually in a core that is not rapidly rotating.
And we know how this configuration arises, that there is this directional rotation after the merger.
Yeah, it's due to the particular dynamics that is kind of embraced. You have this collisional shock, but it's not. It is more that they come together and they develop. So there's a lot of angular momentum, and yeah, it comes from there. So a lot of mass is also brought out by this spiral.
The force here is also the margin of the force.
The courses, but typically they are non-rotating or slowly rotating, and so they retain that.
That is the orbital. So the orbital basically just is transferred to the outside.
Yeah. Yeah, it is. If you want, reabsorbed by this or translated into these arms, spiral arms. It's brought outside. Okay, so this is one of the things that yes, I already said, and I think I will. Yeah, I think I will finish here on this already show. So these are some of my conclusions for today. So where do we stand? I think we have a good handle overall, a good picture, so we know what to look at. This doesn't mean we have understood everything or quantified anything, but I think this is a pretty robust picture, and many groups agree on that. I didn't talk about it much, but for gravitational waveform, we do have complete spectral models, so templates can be used LIGO, Virgo, and telescope. But if you want in particular to infer equation state, like I showed in one of my examples, you don't infer the equation state, you infer either polarizability parameter. Anyway, if you want to use the waveform for probing these effects, which comes at high frequency, the waveform that we have so far are insufficient. And this is an important part. So if you want to build Einstein telescope and you want to say that you're going to do nuclear applications, well, then you have to solve this, or show that you're able to solve this. Otherwise, you don't do any inference. We have a good angle, I would say, of the gravitational dominated phase in terms of remnant, major remnant. Particularly for certain things, we even have quantitative model that we can use in Bayesian analysis to infer black hole formation. But this is not true on longer time scales. So we lose angles and the capacity, predictive power when we go to longer time scale. We have more complicated physics. We have not simulated in details. And in particular, this is necessary to understand the waves, and so to understand the electromagnetic emission. And people are starting now to simulate this viscous space. So there was recently one second simulation from another group. But it's important to improve the physics. Not only to sorry, what group is that? Masaru Shibata group. Okay, I'll stop here and take questions. Thank you very much.
All right, thank you very much, Sebastiano. Any questions in addition to the questions we already had? Maybe from the people online? See, Thomas and Elena are there.
So when you were showing that plot of the MR diagram in our first kilohertz emission allows you to narrow down the maximum. So this mechanism, because typically that correlates to the mass and the radius, and that mass, the maximum.
Yeah, so it was an interesting thing that we realized. People have looked enough in detail at the screens and we would not find anything. And I'm not sure if I have an entire slide on that, but so the way we build the kilohertz and gravitational model is the following. Some time ago, we have realized that some spectral feature of the spectrum are strongly correlated with this tidal polarizability parameter. Here I'm calling kappa, but many people call lambda tilde. And when I mean quasi-universal or EOS insensitive relation, I don't mean that this is independent on the equation of state. I mean that the entire dependence on the unknown equation of state goes into this number. Okay, this is something that people hear often and people that are misleading. Okay. So it means that there is one number or few multipolar number that characterize either interaction in the binary that can capture the broad leading order of physics. Okay? This is what quasi-universal or EOS insensitive means. Of course, it's useful because you only need this number and you can infer this. And so the idea started with the fact that some spectral feature of the spectrum, the frequency domain, they do correlate very nicely with this parameter. And so you can build models, and our latest model is made of wavelets with certain frequencies, certain damping time, and so on, and actually use it to fit. But it's an informed model because given the progenitor masses and radii, you can calculate this and predict.
So, I'm just saying that if I look at the whole waveform that I received from the merger, there are some features of this waveform that only depend on the equation of state through this.
Yes,
kappa.
so this is definitely like this. This is a very.
But let me ask the question.
Yes.
So are those features that are generated once the merger happens?
No.
Or in the inspiral?
No, this is the example. So let's go pre-merger.
Yes, okay. So that I can do.
Yeah, pre-merger we have a complicated Newtonian, but we do have the Newtonian limit. So you have a square interbinary interaction energy, and you have 1 over r. Yes. And if you add the tides, you have this number minus r to the 6, so short range and above. Okay. Now, this is the conservative dynamics if you want, but if you do the simplest leading order approximation, the wave is the same. So you have amplitude, you have a point mass or binary black hole part, and then you have a part which comes from the tide, and again, there is this kappa. So this is super understood. This iterates the higher post-Newtonian order. It's fully included in our EOB models with the summations and so on. So it is valid up to where these effects are attached.
So this is valued in the inspiral phase.
This, in the form, this is Newtonian,
Yeah.
but in the form that we use it, which is not this, it's Violet merger.
Yeah, but once the merger happens,
Once the merger happens, there is then you have to make a logical leap. And well, our leap was to say, okay, that if there is, because we are believer, if there is an Hamiltonian, the Hamiltonian, this goes off record, but if there is an Hamiltonian,
No, it's recorded.
the Hamiltonian, if it's real, can be analytically continued. So if you are close enough to merger, where the Hamiltonian stops to be valid, you can still imagine to analytically continue your Hamiltonian on the other side. This was the idea, right? A bit speculative, I would agree. But it relies on the fact that the emission of gravitational wave is very efficient. And it doesn't take long for merger to wash out all the energy. Okay? So you are still very close to merger. And then what you do, you look at the data. Because you have an intuition, right?
I don't know if I'm correct. One second. You're saying that even once the merger happens, let's say the merger happens at t = 0. So if I ask you about the gravitational wave spectrum generated in the next 10 milliseconds,
Yes, we
are
can
you saying I
fully
can
describe
understand that only knowing the title of the probability parameter?
Yes, this is what we do.
But that,
This is what we do. So
but if that were true, all these things that you were talking about that needs to be included, all these weak interactions, all these magnetic fields, they know
but that's
nothing.
low density. That's
Because
low,
without the probability, I can compute for an isolated star.
yes, but that's low density physics.
That's what?
What I mentioned, and there's ejecta, that's low density physics.
Maybe low density or high density, but it's complicated. It's not just how much the star.
It's complicated
decodes.
physics, but it's not bulk motion of the cores. It's not the two cores bouncing back and forth. It's not one solar mass core bouncing against another one solar mass core. It's more 10 to the -3 solar masses getting away from the core bounce. So there's different scales.
Let me turn it around with the question. If what you're saying is true, and the whole thing is only sensitive to the equation of state through the title of the probability parameter, then we will never learn much about the equation of state because there's an infinite degeneracy of equations.
But
of
this
state
is a
that will give you
possibility.
the same number.
But this is a possibility. So this is certainly true on a phenomenological level. So it's certainly true that you can calculate, you can, based on this idea, it's certainly true, and it's shown here, you can explain the entire post-merger emission of the sample of data that I showed at the beginning with this is faithfulness or with an accuracy that is sufficient for parameter estimation with this idea, with this model. So this is definitely true. Now, whether there is more physics that we are missing or that we cannot grasp, it's possible,
For
right?
example, this statement we make, this, sorry to keep.
No.
this point.
No.
I think
Just
it's
keep on
important.
going.
It's actually a crucial point.
Yeah, because people oversell it.
Okay, so maybe I am a victim of this overselling. because
No,
I'm not
no,
an
no.
expert.
Go ahead.
Maybe I've been oversold, but let me. So I thought that, for example, if QCD has or doesn't have a first order phase transition, is something you can see.
Yes.
Just one second. In one of the peaks or several of the peaks that you get in the post-merger complicated signal.
Yeah.
But that is not included in the title of probability.
Okay. What you're saying is this. So in order, what I'm saying here, so to answer your question, is that you can build a model. Okay? Let's say we can build an accurate model based on this idea. And this frequency turned out to correlate with max density of theory. So that's how we infer the maximum mass. Now, what do we do with this model in a real world where we are interested in phase transition, where we are interested in new degrees of freedom? Well, this model, this particular model, within a few percent of accuracy, includes also some, not all of them, of course, include some equation of state with hyperons and some with phase transition as well. Okay? So this means that we will be perhaps able Well, this means that we will be perhaps insensitive to some of this effect. But if the effect is particularly large and breaks this particular model, we might be able to detect it. So this is the exercise that we did. So for a particularly in that sample, for a small window of masses, we have one equation state librons that at the edge, but breaks that US insensitive relation.
And so what are you calling a model? It's like a set of, what do you mean by it breaks the model?
It breaks the waveform model. So yeah, the waveform model is described.
Ah, you mean that formula you showed.
The waveform model is described by the waveform model is a set, if you want, of frequency, amplitudes, times, and so on, that are appropriately described in terms of not only this parameter, but other parameters. Okay, through and then everything is you build a wavelet basic in this case. So this is the model, and which of course we use the other way to describe this. So in all the sample that we have considered, we know that we have equation state models that do not follow this relation, okay, or that marginally do not follow that relation. So if they break it, you can detect them. And this is an example. It's an example in which you compare these two models here. Same masses, same everything, same equation state and low density, but one contains a phase transition. And you can infer certain these parameters from a spiral merger, they are the same. And you can infer them from the post-merger analysis, and they are okay. And this is what is called in black hole analysis called inspiral-merger consistency check. They do it as GR. You can do it to infer something on the equation state. Of course, you cannot say here that, so there are caveats if you do these games. You cannot say here that I've detected phase transition radials. What you have detected is a deviation from the model. This is where people get.
But here the model is this.
The model is based on a sample of data, say with all hadronic equation state, but of not all possible.
I'll ask you.
Okay.
In all these are you using only the Martian temperature days or to the extent to large temperatures? Because in the post-merger video,
No, these are extended in temperature up to more than 100 of MeV.
Like into the gamma type or
With various different extensions, not really gamma losses. Sometimes it's more sophisticated. I'm also not an expert. I talk to someone and they say, mine is better, use mine. But no, it's not the gamma law. The important thing is that it's not the gamma law. It's something that typically is a bit more sophisticated. To what extent is really the truth?
Can I ask just about the post-merger signal? You keep talking about it as a spectrum, so it's not like a match filter anymore. You're predicting the spectral shape.
No, this is full match filtering.
Okay.
So it's continuous. It's a continuous. So we have templates, and these templates cover. This is another thing. These templates cover continuously everything, and effectively they are made by affecting one body of the plates up to a particular point that is the maximum amplitude. That is the minimum after the maximum amplitude, and then we attach this wavelet thing. But the important thing, it is modeled, so it's not like a bias wave, like a wavelet, unmodeled agnostic analysis. This is all modeled. Okay. So given the progenitor, we continuously attach pre-post in a consistent way, and we do predict whatever comes after. That's the only way you may hope to do physics. So, of course, you want to say, I'm agnostic, I found a signal, good for you. But then if you want to say something about the physics, you have to model something. And so what we have cooked up is something that it's not any agnostic, but it's sufficiently flexible to be at the same level of agnostic searches. This is a very cool thing of the student in particular. He used, so here we have certain certainty, and you use a technique based on the recalibration parameter. So it's the same technique that is used to model noise in the interferometer, but he used it to include in the Bayesian analysis the uncertainty of these theoretical relations. So we do something that is very consistent. When I say we can detect things by a model deviation, it's because we have this recalibration parameter, and we can say there is a model deviation within n sigma. This is very important because this would be tiny effects, special effects.
Question. I want to ask you also that you have talked about the gravitational waves as a probe neutron stars, but to determine basically mass radius relationship or rotation models and so on, do you think there is also a role for other observations, let's say in the X-ray spectra, also the neutron stars or pulsar observations or other things?
Those provide quite those provide constraints as well, of course. I'm not an expert on how exactly those data are treated, but for instance, here they are combined. So what we did in this particular analysis to take prior, this is actually a agnostic prior, assumes only GR, and well, assume three things: GR, maximum mass larger than the pulsar observed, and 170817 parameters. So we added our blue difference based on these two events. Yes, so that's it. But then we could add as well the posterior generated by the NICER, particularly this Miller paper. And it increases the errors as you would expect a bit, but of course it is more realistic because this is our other type of constraint. So you can read, and this as well. So these are not only this type of analysis. All this work have taken very different approaches and even use different data. And you see, they go there and kind of agree. So I think it's quite a robust result by now. This the funny thing is that one of the first, with this work, I think this is gravitational wave only. And okay, fortunately, it has a large error bar because I'm not sure how much this will be compatible with some of the latest NICER observations. And we know why, for example, that work is like that. That's an effect of wave observation.
Okay, so Sebastiano's around tomorrow as well. So if people would like to chat to him, either find him online and contact him directly or come to me. I have a spreadsheet with some meetings that we've pre-agreed.
I'd be happy to talk about this.
Yes, there are a few more slides that we saw flying by. So if you have any questions about that, and come and talk to us. And then I think we should thank him once more for a very interesting talk.